Hello there, I'm Abraham Citizen Ponraj, Assistant Professor, School of Electronics, VIT University, Chennai campus. Welcome to the lecture on ARM assembly programming and introduction. We're happy that you joined the lecture. So, what is this lecture about? This lecture is about ARM assembly programming. So, we'll be having some recap of ARM assembly instructions. We'll be looking at some simple assembly programs. Then we will be programming those assembly programs using Keil IDE, and we'll see some simulation of how the ARM assembly programs would be written works. So which will actually enable you to get familiarized with the ARM instructions. And so to start with, we will look at the first set of instructions, which is called as data processing instructions. So data processing instructions, so before we look at data processing instructions, I will give some small hint of what ARM architecture is about. So ARM architecture is what we call as a 32-bit architecture, and it uses what we call as RISC-based architecture. RISC is nothing but reduced instruction set architecture, and it is also called as a load store architecture. So load store architecture is like, unlike 8051 or any other most microcontrollers, which uses move instruction to access data from memory. But here in ARM, you will have to use what we call the load store architecture to access load and store instruction to access data from the memory. So as in, if I want to get the value from a memory and pass it to my register, or I want to move a value from my registers or as a result and into a memory, I will have to use just load and store instructions. So data processing instructions are instructions which used to manipulate data within registers. So when I'm going to move a value from a register to another register or an immediate value to register, I'll be using these data processing instructions. So we have 16 registers in ARM architecture. So we have from R0 to R15. R0 to R12 are primarily used called as general purpose registers, and R12 R13, 14, 15 are used for some special purposes. So R13 is what we call as a stack pointer, R14 is called a linker, and R15 is what we call as a program counter. So R0 to R12 are the instruction which we have to move data and for any instructions. And apart from all these, we have what we call as status register as well. So we have CPSR and SPSR. CPSR is what we call as current program status register, and SPSR is what we call as saved program status register. So as a matter of fact, so we have around 5 data processing instructions, so they can probably classify it into 5 types. The first is what we call as move instruction. So move instruction, just moving data from register to registers or immediate value into a register. Then arithmetic instructions, so do and add, subtract. So to do that, I have an arithmetic instruction. Logical instruction is basically any logical uh, instructions, say like AND, OR, XOR. And comparison instruction, when I want to do comparison between two register values or immediate and register values, I use compare instruction. We have a separate multiply instruction, so we have long multiply, we have signed unsigned multiplication instruction as well. So we will look into the first instruction, which is the move instruction. So move is the simplest ARM instruction you have, and is the basic ARM instruction we have here. And why we use move ARM instruction? So when I want to move a data from a register to another register or value to an immediate value to a register, I use what we call as move instruction. So let me go through the syntax. So the syntax will remain same, pretty much same for most of the other instructions. So I have instructions So it could be any instructions you have. So in our case, we have move instructions. I would have move instructions. Then I have condition. So condition is another pretty much a unique feature we have here. So unlike what we have in your 8051, where condition mostly comes in association with the jump instructions, here you can have condition along with any instructions. So it is something not mandatory. It can be a part of your instruction as well. So I can have something like move greater than or move less than. So the next is you have prefix s. So s is nothing but S indicates your status register. So if I have a yes along with my instruction, which means that I would have the luxury of updating my status register. So if I don't write an instruction with an S, which actually doesn't update my status register. So this is another thing we have here, and RD stands for my destination register, and N stands for my source value. It could be either an immediate value or another source register. So this is how the syntax looks. It's pretty much similar to all the instructions what we have. And what are the move instructions we have? We have two move instructions. The first is called move instruction. It's a generic move instruction what we have to move values from register or immediate value to register. The next is what we call as move negate. Move negate is another instruction where I can move a not I can move a value which is noted, which would have a not operation first, and then that value will be moved into my register. Okay, here indicates. So if I want to move a immediate value, or register value first, I would note the value, and then I would move the value into my register. So these are the two move instructions we have. The next is about what we call as a barrel shifter. So the reason why we have a barrel shifter as a part of, along this assembly programming is that the barrel shifter enables you to do what we call as pre-processing. So pre-processing is nothing but it helps me to pre-process a particular register before I come into my ARM arithmetic logical unit. So before I come into my ALE, I can do a pre-processing, and that is done with the help of barrel shifter. So barrel shifter does some shifting operations. So we have some logical shift left, logical shift right, rotate, right, and all those instructions can be done using your barrel shifter. So in most of the other controllers, you will be doing your shifting operation as an individual entity or an individual instruction. So this can happen with your move instruction as well. And what is the advantage? So this helps you achieve fast multiplies or divisions by a power of 2, and that is the big positive we have here as a barrel shifter. Oh, here's an example. So we apply a logical shift left to register RM before moving it to the destination register. So this is the same as applying a standard C language shift operators. So standard C left shift operators happens to register, and that is the same with logical shift left. So the move instruction copies the shift operator results N into RD, and the N represents the result of the logical shift operation. So what is the instruction I have? I have so a pre stands for condition of my registers before processing, and post is after processing. My instruction here is move. I have no conditions here. I have no S here, so which means it doesn't update my status register. I have two registers, R7 and R5. So R7 is my destination register. R5 is my source register. And I have an operation which is called logical shift left true. So before my R5 is moved into R7, my R5 is shift twice to the left and then moved into my R7 register. So as a result, my R7, 5 which has 5 is shifted twice. So basically it's the power of 2, so I would get 20 saved in my R7 value, and my R5 value would remain the same as 5. So that's the advantage we have using with the help of barrel shifter pre-processing. Okay, here's what are the barrel shifting operations we can do. So I have 5 barrel shifting operations. I have logical shift left, logical shift right, arithmetic shift right, rotate right, and rotate right with extent. So these are the basic barrel shifting operation you have. So the example what we saw about logical shift left. So about logical shift left, and you can also use any of these instructions as a pre-processing instructions. Okay, so what are the next data processing instructions? What we call as the arithmetic instructions. So I have about 6 arithmetic instructions, and so all of them are 32-bit values. So I have add with carry. So the basic is remain the same. Add with carry, it adds two 32-bit values and the carry. A simple add which just adds two 32-bit values. Then I have a reverse subtract of two 32-bit values. I have a reverse subtract with carry. So so reverse subtract is just going to be that this n and Rn would be shifted. So will be like n minus Rn. Here it is. So reverse subtract says is n minus Rn. So reverse subtract with carry. So n minus Rn minus carry flag. And I have subtract with carry, and I also have the normal subtract. And I can use a barrel shifting here as well. So what are the logical instructions I have? I have 4 logical instructions. I have an AND, I have an OR, I have an XOR, and I have a bit clear. So these are the 4 logical instruction I have. So AND, OR, XOR, and bit clear. So AND, OR, XOR is very simple, does the basic logic operations. Bit clear does an AND and a NOT. So here's your destination RD, here's source register 1 Rn, and you emit value n. So Rn and a NOT is moved into my RD register. So comparison instruction is an instruction which is used to compare two values. So it could be a register or immediate 32-bit value as well. So the update of a CPSR flag bits according to the result, but it does not affect the register. So previously I was telling you, if I have an S as a suffix, what it would do is it would update my CPSR value. So the comparison instruction compares a register with a 32-bit value or two registers. So they update the CPSR flag bits according to the result, and they don't affect the registers what we use. So if you remember correctly, I said that suffix x is needed. I think I said prefix is actually suffix. Suffix x is needed after every instruction to update the CPSR. So when I'm using comparison instruction, suffix x is actually not necessary. It automatically updates my CPSR values as well, or my flags. So we have 4 compare instructions. The first is compare negate. We have compare, we have test equality, and we have test bits as well. So compare negate, compare, test equal, and test as well as the test. equal and test or something. Test equal does an OR operation and test does an AND operation. Whereas compare does a negative operation and subtraction operation, and compare negate does a addition operation. So next instruction would we have multiply instruction. So multiply instruction is primarily used to multiply values. So here we have multiply accumulate and we have a multiply instruction as well. So multiply accumulate multiplies and then it adds another value to it, whereas the multiply instruction just multiply two values. So multiply accumulate, Rm is multiplied with Rs, then it is added with Rn. So whereas multiply is just multiplication, and we have a few other instruction. One is called as signed multiplied long, just signed multiply accumulate long, unsigned multiply accumulate long, and unsigned multiply long. So these are the various multiply instructions we have. Here are the branch instructions. We basically have 4 branch instructions: a simple branch instruction, a branch with linker, a branch exchange, and a branch with linker with exchange. So branch instruction is primarily used as a simple branch instruction where my program counter value will be updated with the label I have, and a branch linker would have the label in my program counter, and the linker would have the return address where it should come once the subroutine has been serviced. Then branch exchange and branch linker exchange are used when I'm going to go from my ARM architecture instruction set architecture to my thumb instruction set architecture. So what's a thumb instruction set architecture? A thumb is a 16-bit architecture. A thumb is a 16-bit architecture, whereas ARM is a whereas my ARM is a 32-bit architecture. So when I want to exchange from my 16-bit architecture to my 32-bit architecture, I use my branch exchange. And branch linker with exchange, again, my linker would have my location where I should return after my subroutine has been serviced. Okay, so now we have about 15 conditional instructions. We have about 15 conditional instructions which can come along with any of those instructions what we have, or it can be used to the branch instruction like what we do in many other uh, instruction set architectures. So what are they? I have equal, not equal, equal, not equal. Then I have what do I have? Many other equal, not equal. I have various other greater than equal, less than, greater than, less than equal, and I also have some basic other comparison I have along with what we call as AL. AL is nothing but it says always, which is used when I don't want to have any conditions. So it would run any other program as well, any other instruction as well if I use AL. And the associated flags is given as well. So when, for example, if I do a compare equal, it checks my 0 flag, and a less than check a negative flag, and greater than check would if 0 is clear in a non operation, and less than equal to see if set is set in non operation. Okay, here's load store architecture. So load store architecture, I said whenever I want to do a memory access, I would be using what we call as the load store architecture. So load instruction is for basically use load and store instruction basically for moving data from a register to a memory or a memory to a register. There are 3 types of load store instructions. First is called as a single register transfer, multiple register transfer, and a swap instruction. So single register transfer is when I want to transfer a data from a value from a memory into a single register. Or multiple register transfer is when I want to transfer a set of values into a set of registers, or a set of register into a set of memory location. That is what we call as multiple uh, register transfer. And the next is what we have a swap. Swap is the basic operation where I want to swap a memory value with a register, or register with a memory value. So these are three basic load store instructions we have. And load into register, store into register, load byte into a register, store a byte into a register, load half word, save a half word, load a signed byte, load a signed half word. So apart from, if I use LDR, I would be using to load a 32-bit value. If I'm using LDRB, I'll be using to load a byte, which is an 8-bit value. So if I'm using LDRH, I'll be using to load a half word, which would be a 16-bit value, and similarly for my signed byte and signed half word. So multiple register transfer I'll be using when I want to do a multiple register transfer. I'll be using LDM. My LDR would be made into LDM, which says multiple register. So I have my instruction condition, and I have certain addressing modes with my multiple instructions, multiple load instructions, which can be used. And Rn with the explanatory mark says my register would be updated, and what are the registers I want to transfer the value to, or transfer the value from, would be given in curly braces. And again, swap instructions, we have two swap instructions: swap a word and swap a byte. So swap a word stands for swapping a 32-bit value, whereas swap a byte stands for swapping a 8-bit value. Okay, so we'll go to the first program. So first program is going to be programming x is equal to a plus b minus c. So this is a simple program what we write. So what I've done is I have moved value into A, which is going to be the memory location. And I moved that into register R4, and that value is loaded into R0. So once I've done that, then I have similarly I've done a B value. Okay, so it's supposed to be B. So I store my B value into R4, and then again my R4 value is moved. The memory location, whatever is the memory location, was moved into R1. Then I do an AND operation, and R3 comma 0 comma R1. So which basically adds R0 plus R1 and store that value into R3. So again, the next is going to be a subtract operation. So I'll have to get the value for C. So I load a memory location to R4, and then I load the value in the location into R2, and I do a subtract operation. Subtract R3 minus R2, and the value is stored into R3. To store the value of X, so I load a value in memory location to R4, and that value R3 value is loaded into my R4 memory location. So what we'll do is we will write a simple program using Keel. We'll write the same program using Keel, and we'll execute and see how it works. It's my Keel software. open it. So what I'll do is I'll create a new project. New microservice project. So I would give it as lecture. So I've created a file called lecture, a project called lecture. Okay, now I'll have to choose my ARM architecture. So what I do is I would go into my legacy device database instead of going to my software packs. Then I just choose an ARM7. It could be any or any of the ARM7. So it could be either an NXP's LPC 2148 or it could be anything. So I'll go with the generic ARM7 with big Indian architecture. Click OK. Okay. So now you'll have to write your program. Okay, so I go and click my program. Click document to write my program. So you have some derivatives to be followed. So I will write define an area. B area. I'll give a name. So let me say I'll give it size 1, comma code, comma I'll give it as read write. And I will give an entry. Okay. So what we did want to do was x equal to a plus b minus c. That's what we wanted to do. So we'll write the program for that. So I just write move let me say r4 r4 comma a it's ldr load register, load a single register. So it's ldr and I have to move my r4 has the memory location for a. So in that location I have the value of a. So I'm going to write ldr, let me say r0 comma r4. So always my memory location is written in square braces. So again I go ahead to get my b value. Let's move r4 comma I cannot use a b value as a because I have b for branch. So I would be using d. We're going to use d. So I'll change this into a plus d. Then I'll use ldr r1 comma r4 in square braces. Then I'll write. Okay, so I've moved the values, so I'll have to add a plus d. So add. So I can use a s here. So an s would update my CPSR, and if I don't use an s, it doesn't update the CPSR. So I can do an s. R. I would say right. R0 comma R1 comma R0. Okay, so I've done the first summation, and the next I should subtract the value of a plus d with c. So I'll have to get my c value, move 4 comma c, write ldr r0 okay. So I've done all these, so I'll have to do subtract operations. Subtract. If I want a CPSR update, I do an S. If I don't want, let me just not do it this time. And I'll have to do subtract R1 minus R0. Okay, sorry. R0 has, so I'll make this as R2. So let's subtract R2, comma R1, R2. Okay. So I've done the move and subtract operation now. Now I'll have to save the value, save the result in. I have to save the result in X. So let me get the location for X. Move R4, comma X, and then load register R3, comma R4. So sorry, I have to store register R2 in the location R4. So I've written the code. The code is written. So I'll have to give a stop condition. So to terminate it, I just give stop. So a simple jump operation. Branch stop. Then a simple operation. So similar to the sjump operation what you give in 8051. And now I'll have to define my values for A, D, C, and X. So again, I'll have to write this. Just write this. A values equal derivative EQU, and my location 0x 0 0 0 0 2 0. B, sorry, it's not B, so it's D. 0x 0 0 2 4. So I'll give a loss location to 0 as well, so you can see in a single window. So I've written the code. I have to save it. So I save it as .s file. So S stands for assembly, and I just save it. Okay, it's all fine. Okay, now once you have saved it, you'll have to add it in your source group. So I go add existing file, and then I select source, and then I write my source group. So what is my source group here? What did I save it as? I saved exercise. So yes, yeah. So say I add it, and I close, and you go save it here. You'll get it. Okay, you created your program. You've saved it, added it in your source group. You'll have to compile build. Okay, it says 3 errors. Okay, missing area derivative, so where is it in capital? And I just write the end here. Okay, it says 0 errors and there's 4 warnings. You can just ignore your warnings. Okay, so writing this as such is very important. You don't miss. It's quite case sensitive. So I have area, code, read write. So I'm writing. I may have two different types. Yeah, I can have a code. I can have a data. So I've used code here itself. So it enables you to access the memory. So when I use the data, I would have trouble accessing my simulator memory. So I just use code here, and read write. So read write enables you to read and write, or I can have only read only. By default, it is read only. So let me go to debug. Okay, so I'll have to go and write the memory value. I'll have to give a memory value 0x00, sorry, 0x000020. Okay, so there's already some values there. So what I can do is I can give some value here. Okay, I can give some value. Okay, it's not updating, so which means I'll have to go enable them. So I write memory map, go to memory map, I go to debug, go to memory map, and then I choose the memory range I need. So write 0x, 0x, 000, and 0, comma, 0x, 0x, 000, let me say 30. Read, write, and execute. So I'm giving all the access, give map range, and then I hit close. So let me give some value here. So it's 20 here. So I give 02 here. And my A value, my D value, and now my C value. Okay, so let me give 01. Okay, so I loaded the values. So let me run step by step. Okay, so you can view your access here. So it gives my CPSR. So here the registers are 0 to R15. They are 0 to R12 are a general purpose register, whereas R15 is my program counter and R13 is my stack pointer. R14 is my linker. And I have my CPSR, which says my flag, and my SPSR as well. So, okay, so let us run. So remember, if there's an S, it updates your flags, else it doesn't. So our 0A value, which is 020, it should be loaded into my this location R4, which is loaded here. 20 is what the value I've given is loaded here. Okay, so 20 is moved. I have my value 20 is moved into my location R0. So I get the next value, which is 24. D value is loaded into R4, and location value, which is 2, should be loaded into my R1 register. Okay, I get 2. So now I'll have to do an AND operation, R0, R1, R0. So my R0 will have the result. So I have it here, 22, R0 has 2, and now I'll have to get my C value to do the subtraction. So C value is at location 28. So my location 28 is moved, and the value 1 will be moved into register R2. So it's done. Now I have to do a subtract operation. So I do a subtract operation, and the result should be stored in R2, which size is 1. Yeah, moved. Okay. So I'll do it once more. I think my store operation was in the zero probably, so just go ahead. Once more with the predefined values I have here. So I just load it, and the value is being loaded here. You see all those values loaded. And then I do a subtract operation, and my x value is loaded with 20. And my x value should be updated with the subtract value, which is FA84 2002. Okay. So my value is stored in my location. Okay. So that's a simple basic operation. I think we still have trouble saving the value in your location. So we'll go ahead to the next program, and probably we'll sort it out then. Sorry. Just hold on. Does it help? Doesn't. Okay. So some small probe. Okay. Sorry, I've not done a debug file. Give me a minute. Debug settings. Sorry. Cancel. Memory map. So it goes to 0x 00000. Come on. Yeah, it's 0. Yeah. So my R2 value is successfully stored in my R0 value. So yeah. So we got it right. So we'll go to the next instruction, next program. That's what we'll see. So program 1 is a simple basic program. So program 2 is with multiplication. So it's again the same with the multiplication operation. So uh, so simplest of program what we have. So the program 2 is pretty much a simple program which has y is equal to a into b plus a. This is again a simple program where I'm going to load the value for r0, r1, and then I'm going to add those values with r3, r0, and r1, and then I'll be loading a value for multiplying with my r3, r3, and r2, and I would go and store the value. So what I would do is, instead of doing it all over again, I will just execute the program which I've already created. So it should save some time. Sorry. So project, open project, and then I'll go for, here I've created most of the programs. Okay, so the other case, what we did was we actually loaded the value. We loaded the value, and the memory location we gave the value. We loaded the memory location and we gave the value. So here I'm just loading my value, constant value. I'm just loading my constant value in our case. Our case was like, say y is equal to a into c plus d. So c plus d. So this was our execution. This is what we want to do. So what I've done is I've loaded a constant value for A, B, C, A, D, and A, and I've saved that into a memory location. So I'll remove already existing file, and I'll load my file, which is ads.s. ads. Okay, I've done this, so got it here, and now I have to build it. Says no error. Now I can go and debug. Fantastic. So I've come to my debug, and I have my memory location here. I just go and make sure my memory map has write access as well. So I write 0x0000000, comma 0x00000 to b. Read, write, and execute map range, close, and let me know the value. So C is loaded with A, which is 10, and D is loaded with 6. So A plus 6 gives me 1 0, which is in R3, and then I'm going to get my A value, which is 5. So it's going to be 5 into 10. So my value 50 is stored in location R2, and I'll have to store that value in a memory location 20. So okay, so I have 50 stored in my memory location. 50 is my memory location 20. So it's as simple as that. So we have seen how to give a value in the memory and store it, and value using equation, and then storing the value in the memory location. So we've loaded the value directly, and we can also load the value through memory. So that is the second program. And the third program is to evaluate a little bit a complicated one where it says I'm going to have A 8b plus 7c minus 27 divided by 4. So this is my instruction. So I don't have a divide instruction. So to do a divide instruction, I'm going to use a substitute instruction. So yeah. So this is my code. So I'll just take the equation. Okay, remember, ARM doesn't have a divide instruction. To do a divide instruction, I'm going to do a arithmetic shift right operation twice. Okay, so this is again a barrel shifter operation. So I write move 25 because if you look at it, so A is equal to 25, B is equal to 19, C is equal to 99. Okay, so I write 25, I moved into register R0, and 19 I moved into register R1. So I'll have to write add B8 into location with A. So for that, what I've done is I've done a shift operation here. So I've done a logical left shift thrice. So each time a shift is multiplied by 2. So I don't have to use a multiplication instruction here. So to make things faster, I just use the logical shift left. And that's the advantage of barrel shifter. So I've done and add R0, my destination register, my first source register R0, which is 25, R1, which is nothing but 19. So I have to 19 into 8. So to do that, I've done it thrice. I've done a logical shift thrice, and then I have done an addition. So then next is I have to take my next value, which is C, which is 99. So I have moved C into register R1 and then 7 into register R2 because I have to do 7 into C. So I do multiply accumulate. So what I've done, I've already had the addition value here. So I multiply my R1 with R2 and I add that with my value here and R0. So which completes our first 3 sections. Then I have to subtract the value of 27, straightforward instruction I subtract. So once I have done this, I have to divide my R0 value by 4. To do that, I do an arithmetic shift right with #2 twice, so it gives my division value. Okay, so compile, no error, so instead of go into debug, sorry. Okay, I have to add my value, which is SDA. And then I remove my previously existing file. Now I do a compile. It says 0 error, 0 warning. You can go ahead. Just Okay, so this my values in hexadecimal. Okay, I do a logical shift thrice, so my R0 value become B1 and all the rest remains the same. So I move 99, 63 into R1 and then I move 7 into R2, then I do multiply accumulate value. So my result become 366. So now I have to subtract my R0 value 27. So I get 34B and I do a division operation with 4 with the help of arithmetic shift right. So my first instruction if I'm using a barrel shifter would be this to be executed, followed by this. Yes. So my value R0 is nothing but D2 is my answer. So this is a simple instruction where we use logic. We use a barrel shifter for the multiplication and division. And as I cited, you don't have a division instruction, so you use ASR. And instead of using a separate instruction multiply, which I'll have to use it here, I have just straight away used the entire thing in one simple instruction. So as a result, you get better code density, and your processing is done a little faster than the usual. Okay, that's my third program, and my fourth program is another interesting program. So how I'll be using conditions here. You're using your compare instruction and conditional execution here. So we'll be using this C program, higher level program into, we're converting this higher level program instruction into a assembly instruction. So if you see here, I have a if condition. I'm checking if I is equal to 0. So that's my condition. Then I'm going to do I is equal to I plus 10. Else I'll be doing I is equal to 10. So it's as simple as that. So to check the condition, I can either use a compare. I can use the compare value, and then I can check my condition. So what I'm doing here is I first move 0 into R1. So subtract is just one method of making sure that R1 has 0 value. So I'm comparing R1 with 0. So if R1 is equal to 0, then I would be doing add R1 comma R1 R1 comma 10. If it is not equal, I'll be moving a negative value R1 comma I'll be moving, if it's not equal, I'll be moving 10 into R1. Okay, this is the code. So this is what we want to do. So let me this ABS. Okay, close. And I don't want to do this code. Okay, so says error. I'll go ahead to debug. So you see, I has I is loaded. I has a memory location that is loaded into R4, and R4 is loaded into R1. So you'll have to give your I value. It could be 0, 1, 2, 3, it could be any value. And then I'm going to compare that value with R1. And if it is equal, it adds R1 with 10. If it is not equal, it moves R1 to 10. So what I will do is I would actually okay. So let me first do my memory map. So make sure. is O here. Okay. So let me give a value as so to compare R1 with 0. So they're not equal, so I'll have to move R1 as 10. So I move R1 with 10 and then I store the value back, which is 10. So I store the value back into the same location. So the simplest of if a conditional execution what we have here, and the next is another sentence. How do I execute a for loop? So it's again very simple. I just make sure my R0 value is 0. So I say I is equal to 0. I make sure my value is 0 and then I compare and I keep adding. If it's less than, I'm going to add j plus j. And again I would be adding. If it's less than, I would be incrementing I. So I'll keep incrementing and then I give a branch less than star. So as long as it's less than, this loop will keep executing, and once it's become greater, this loop will end and it will stop your code. Okay, so the next is a simple execution where again you're going to check a condition. It's a while loop, so we say if, for, and while. So while a is not equal to b, so you have a condition. If a is greater than b, I have a minus b, and if it's less than b, I'm going to have a b minus a. So there are two ways of writing the code. I can either write it with the help separately with branch and conditions, or I can have it with along with my instruction. I can have my condition with instruction. If you look at this, the number of instruction lines I have is reduced by 3, reduced by 4, reduced by 4. So that is some very huge reduction in my instruction lines. So again here, so my first condition is to do while a is equal to b. So if the first condition R1 and R0 and R1, so I'm checking if they are equal. If they're equal, you're going to halt. If they're not equal, I'll do my first two cases. Where I give branch less than if less. So I'm going to do R1 comma R1 comma R0. So then I do again subtract R0 comma R1, do a subtract operation, and then I go back and I keep doing it again. So it's just first if A is greater than B, I'm going to do A minus B, else I'm going to do, so I've just checked. If it's less than, I'll do B minus A. If it's greater than, I'll do A minus B. So that's the thing. The same thing I've done with conditional execution along with my instruction, so it's reduce my code. So the next is a Boolean operation. So logical operation. So logical operation, I have my AND, R, and move, negate, and my bit clear instructions. So we'll just check this instruction: A and B plus C, A and B are C and C and D complement. So this is the thing what we're going to do. I think I've written code for this. Eh, Okay. So I think I've written the code for this. I've written the code for this. So this is another Boolean operation where we're going to do a logical shift left twice, then I'm going to do an OR operation with B and 15. Yeah, so here's my Boolean, here's my instruction, so I'll add them. There's no errors, you can ignore the warnings, so we'll just go ahead. So you have to change okay, got it right. So a value we'll just keep use a pre-existing value already. Yeah. Cool. So the first value is loaded. The next, okay, I have logical shift twice. So I've done the first operation. I shifted it twice, and then I'll have to do an AND operation with 15. C and 15. I get C value, and I'll have to AND that with 15. So I get my value as E. Now I'll have to OR my first value with the second value. So R0 or R1. Okay, so that's done as well. And the result is in R1. And now I'll have to move the value into a location. So the value is moved to the location as well. Okay, so it's a simple program, simple Boolean operation what we have, and it's been executed. The next, we'll go for the next instruction, which probably could be the last. Okay, so here's a big condition where I say if a less than b, if a less than b, x is equal to 5, y is equal to c plus d, else x is equal to c minus d. So I can write this code in two ways. One way is using instruction with, like how I've done it, instruction with condition, or I can just write two cases. So if less than b, I do conditional execution once, all this, else I can do another conditional execution here. So having instructions with conditional execution makes my program much smaller and help in making an effective programming, and having conditional execution separately would increase my code length, and I would have very less memory space left. So having using instruction with conditional execution is the optimal way to write this code, and so I've taken that, and which eventually ends up in around 15 lines. So I've done the same thing here. I've moved the values for x, y, for values y, c, d, and I've given locations I moved. I've done the comparison operation first, and based on that, I've done, if it's less than, do all these operations, and if it's greater than, you'll do all these operations. So the simplest code, and so what we have seen in this lecture is we have seen about some basic ARM instructions, and we have also seen some basic ARM codes. So which sums it all, and I hope you had a wonderful time, and take time to go and Try down all the programs in your key and feel free to ask questions. Thank you and bye for now.